All right, so if we have qualitative data about more than two population proportions, we're going to use what's called a chi-square test, or it's also called a goodness of fit test. Both of those terms are used interchangeably. Now that kind of funny little X that you see there, the X with the little flare on the end, that's not just an X, that is the Greek letter chi. And so the chi-square is the chi with the, squared, the 2 up above. So I know we're getting into where we have X's and we have little X's and big X's, and now we have these chi's that look like an X but aren't an X, so just keep that in mind. So the chi-square distribution is similar to that Bernoulli distribution, the binomial distribution that we looked at in several chapters ago. I believe it was chapter 5, where it's a family of distributions. So the chi-square distribution depends on degrees of freedom, where degrees of freedom is calculated as the number of groups or the number of samples that you have, or what we call K minus 1. And so the chi-square distribution, again, it's asymptotic. It goes almost to 0, but not all the way to 0. It is always positive, though. You can't have a negative chi-square. And so it is always positively skewed, which means it skews off to the right. And then the larger the degrees of freedom, the more closely it approximates a normal distribution. So we'll look at that on the next slide. So here we can see if we have fewer degrees of freedom, like the green here, that it's very positively skewed. And then as we get 10 degrees of freedom and then 20 degrees of freedom, it approaches more of a normal distribution. Now, we're always looking for probabilities in the right tail. We're going to be specifically doing a right tail test. So we're always looking for the probability that it is greater than our test statistic. Okay. So again, we looked at this Bernoulli process in an earlier chapter. We're looking at, this is again what we call a multinomial experiment, where we're looking at, what happens to the stock price? How would we rate customer service? What's the probability that a student's going to pick to major in accounting versus majoring in management, things like that. So we're kind of categorizing, we're looking at what is the probability that a student's going to fall in one of these categories. So again, K is the number of possible outcomes. The probabilities of all of the possible outcomes do have to add up to 1. Remember, we learned that when we talked about probabilities. Probabilities always have to add up to 1. So the null hypothesis is that the probabilities are either equal to each other, such as we have here in the first one. So we have probability 1 is equal to probability 2 is equal to probability 3 is equal to the probability of 4, which all equal 0.25. Now it's 0.25 because there were 4 probabilities. And so if they're all equal, then they are all 25%, or 0.25, because they have to add up to 1. If we had, for example, 5 populations here, then we would say that they were all equaling 0.20. So remember, they all have to add up to 1. So our alternative hypothesis is just that not all the population proportions are equal to 0.25 or equal to each other. We're not going to say that they are all different. Notice that. So as long as one of them is different, we would reject the null hypothesis. So for example, if the probability of population 1 is different, but probability of populations 2, 3, and 4 are all equal, we would still reject the null hypothesis. So just because we rejected the null hypothesis doesn't mean that they are all different. Now we can say not that they're all equal, but maybe that they all equal some expected value. So here we have, in the second example, we can say we are hypothesizing that the probability of population 1 is 0.4, for population 2 is 0.3, for population 3 is 0.2, and population 4 is 0.1. Notice again, if we add all that up, it all equals 1. So the alternative is just that not all population proportions equal their hypothesized values. Again, not that all of them are different, as long as one of them is different. If the probability of population 1 is not 0.4, then we would reject the null, even if 2, 3, and 4 were exactly spot on. So need to keep that in mind as we're making our test and drawing inferences from this. So we're going to be looking at an example where we have So we're going to be looking at this example, sorry, I wanted to skip that other one, where we have 5 companies that manufacture a particular product. Maybe it's a cell phone. We're not really even told what it is. Maybe it's a small SUV or a small crossover SUV, but they all manufacture the same product. And we have their market shares in 2010, and then we're going to look and see if those market shares have changed recently, assuming a 5% significance level. So this is the data that we're given. We have the 5 firms, we have their market shares in 2010, and then we have a survey of 200 recent customers, and we ask them, hey, where did you buy your product? And they told us, and so we've sorted those out between those 5 firms, and we're trying to see, based off this recent sample of 200 customers, if this is different, statistically different than it was in 2010. Can we say that the market share has changed since 2010? Now let's walk through our steps, and then we're going to jump in Excel and actually do this. So the first thing that we have to do is calculate what the expected value is based on our 2010. So, well, actually, first we have to state our hypotheses. So our hypotheses are that they haven't changed since 2010. So the probability of firm 1 having 40% market share, firm 2 having 32%, 3 24, 4 2%, and 5 2%. So our alternative is that not all population proportions are equal to their hypothesized value, that something has changed is what we're hypothesizing. So we can first calculate our expected frequency. So I've got this printed here, but we're going to jump into Excel where I think it's going to be a little bit easier to see. But first we want to calculate our expected frequency. So our expected frequency is the current survey of 200 people multiplied by the probability of each category. So if firm 1 is expected to have 40% of the market share, then we would expect 80 out of these 200 people that we just surveyed to have bought firm 1's product. If firm 2 is expected to have 32% of the market share, then we would expect that 64 out of the 200 people that we surveyed would have bought firm 2's product. And then you see that we go on to firm 3 with 24%, firm 4 with 2%, and firm 5 with 2% also. So then we can compare these expected values with what our sample actually showed. Now, if you notice, we see that the expectation for firm 4 and for 5 were 4 customers each. We expected 4 out of the 200 people to buy in firm 4's product and 4 out of the 200 people, to buy firm 5's product. Now, the chi-square test doesn't work with really small frequencies. So any frequencies less than 5, we're going to have to combine together. So we're going to group 4 and 5 together and to say, all right, we're expecting 8 people, 8 out of the 200, to have bought either firm 4 or firm 5's product. So we have to combine those together so that everything's greater than 5. So now we need to revise our hypotheses. So our new hypothesis is that firm 1 is 40%, firm 2 is 32, firm 3 is 24, and now firm 4 and 5 together, we're just going to lump those together and call that the probability of 4. That's 4% now. So that's the 2% for firm 4 and the 2% for firm 5. We've added those together to calculate that combined probability. Now, our test statistic, this we do have to calculate by hand or in Excel, so you're going to want to make sure you write this formula down. So, it looks hairy, but I promise it's not. So for each of the firms, we're going to take the original, the surveyed value, that's O, that's the surveyed statistic, minus the expected value, that was what we just calculated, square it, and then divide it by the number of expected in that category. Okay. So when we do that, we get a chi-square statistic of 10.250. As again, we're going to calculate this in Excel in just a moment, but I want you to write the formula down. And then we could look up in a chi-square table, or we could do a calculation in Excel to determine the p-value. So I think this is where we're going to jump over to Excel. Now, we don't have a workbook for Chapter 11, but I went ahead and entered the data. So this is the data that we have, and I've entered the original null hypothesis and alternative hypothesis here. So first of all, let's go through and calculate our expectation. So I'm going to do that here in column D. So my expectation is going to be the market share. Oh, actually, before we do that, I want to back up a minute. Let's test, first of all, let's make sure that our market shares all add up to 1, which they do. And let's make sure that our number of survey customers adds up to 200 like we think it is. All right. So now I can jump back over here to my expectation. So my expectation is going to be, for firm 1, that 40% of the 200 total customers are going to buy firm 1's product. So that's 80. Now here's what I can do. I'm going to go up to my formula, and I'm going to, within the C7, I've clicked inside the C7, I'm going to press F4 to make that an absolute cell reference. And now I can just drag this down. So now it's going to multiply, we see B3 times C7, and B4 times C7, and B5, and B6 times C7. And then I can again add these up, and by the way, they should equal 200. If they don't, we know we've made a mistake somewhere. All right, now we've already talked about, since firm 4 and firm 5 are less than 5 each, we have to combine them. So I'm going to just change this up here. Instead of this being 0.2, I'm going to change it to 0.4. And instead of this being 10, I'm going to change this to 16. And then, I know it's messing all my formulas up here, but I promise it won't, because now I'm going to delete that. Oh, look, and see, now it all goes back. So now I've combined 4 and 5 so that my probabilities all still add up to 1, my total survey still adds up to 1, and my to 200, and my expectation still adds up to 200. Now I need to come down here and change my null hypothesis. So I'm going to delete the P5, and I'm going to say P4 is equal to 0.04 or 4%. So again, we've had to update that to make sure that they're always greater than 5. You want to highlight, star, triple underline that in your notes. So now I'm going to go through here, and I find it easier to do it this way. I'm going to go through here and calculate the squared difference. All right, so the squared difference is going to be equal to the survey response of 70 customers minus my expectation. Ooh, I didn't put my parentheses in. Got to put my parentheses in. And then I'm going to square that. So I'm going to use my little caret. That's the number on top of the symbol on top of the 6, and square it. So if we can think about this mathematically, there's a difference of 10. If I square it, that's 10 times 10, that's 100. So now I can just drag this all the way down through my 4 firms, my 4 categories, and I've got the square difference for each one. So now I can come down here and calculate my chi-square test statistic, which is going to be equal to, remember, it's the sum of each one of those squared differences divided by the expectation. So it's E2 the squared difference for firm 1 divided by the expectation of firm 1, plus the squared difference of firm 2 divided by the expectation of firm 2, plus the squared difference of firm 3 divided by the expectation of firm 3, and finally plus the squared difference of combined 4 and 5 divided by the expectation of 4 and 5. And so we get 10.25, which is our test statistic. So we could again look that up in the table, or we can go ahead and just use the chi-square formula. So we're going to calculate our p-value by using the chi-square formula. So again, I'm just going to start typing it in because I know what the formula is. But you know, we can go up here to formulas. We can use statistical. And here we see chi-square, and we notice that there's a lot of them, right? We want this chi-square distribution right tail. Now notice it's going to ask us for the x value, that's the test value, that's the 10.25, and the degrees of freedom. Remember, the degrees of freedom is k minus 1. It's the number of categories, if you will, minus 1. So since we now have 4 categories because we had to combine 4 and 5, our degrees of freedom will be 4 minus 1, or 3. So my x value is C11, and my degrees of freedom, I'm just going to type it in, is 3. But remember, your degrees of freedom are always k minus 1. And so here I get a p-value of 0.0165563. So if we have a 5% significance level, since the p-value is less than 0.05, we can reject the null hypothesis and say that the market share have changed since 2010. The market shares are not the same as they were in 2010. Now, notice that this test does not tell us which one has changed. It doesn't tell us how many have changed. Have all 4 changed? Has just one of the 4 changed? If it was just one of the 4, which one was it? Was it 2 of the 4? Was it 3 of the 4? We don't know. All we know is that the market share is different. Okay, that's all we can say. We can reject the null hypothesis that the market share is not the same as it was in 2010, but we can't draw any other inferences from this.